Hello and welcome to the 13th of our NASA Engineering and Safety Center Guidance, Navigation, and Control webcasts. I'm Neil Dennehy, the NASA Technical Fellow for Guidance, Navigation, and Control, and I'll be your moderator for today's webcast. As I have previously mentioned, the idea to have these hour-long webcasts originated with the members of my NESC, GNC technical discipline team, who thought they would be a good way to broadly share their individual knowledge with the rest of the NASA GNC community of practice. We nominally hold these GNC webcasts on the third Wednesday of every other month at this same time, 2 p.m. Eastern. Please note that the webcast is being recorded and will be made available for subsequent viewing on the NESC Academy site. The link to the NESC Academy site can be found on the webcast registration page. And now I'm pleased to introduce today's speaker, Dr. John Christian. John is an aerospace engineer with expertise in spacecraft navigation and space systems. He is presently an assistant professor in the Department of Mechanical and Aerospace Engineering at West Virginia University. John has experience with navigation system design, flight tests of relative navigation sensor hardware, for example, the STORM VNS or Vision Navigation System LiDAR experiment on STS-134. Also experience with parachute drop tests, inertial measurement unit data processing, and system requirements definition, as well as space systems analysis. The complete version of John's biography is provided on the webcast registration site for your reference. John's talk today is entitled Fundamentals of Vision-Based Navigation. This is a topic of growing interest and mission application within NASA, so I think this is a very timely opportunity to get to hear John's insights. At the end of John's talk, I will moderate a 10-minute question and answer period. You will be able to submit questions to John on the webcast site. I will now briefly walk you through the mechanics of how to do that. If you look at the snapshot of the webcast panel now being shown on the screen, you'll see an expanded look at the toolbar at the bottom right. There are two specific control buttons on that toolbar that I want to draw your attention to. The first is the Ask a Question button, which is the third button from the left on the actual toolbar. At any time during the webcast, you can use that control button to submit questions to John. Please include your email address or simply your name and center location when you're submitting your questions. Because of the 10-minute time constraint for the Q&A period, John will most likely only be able to answer some of the questions that he gets from the audience today. However, as long as we have your email address or your name and center location, John has promised to respond to all questions that he receives today. So I encourage you to submit your questions during the course of John's talk as they pop up, rather than waiting to the very end of his presentation, as I'll be collecting them up as we proceed through the talk. The second feature on the toolbar I want to highlight for you is the volume control button on the far left. If you place your cursor over the speaker icon there, you can access the volume control slider and use that to individually adjust your computer speaker volume appropriately. And now I'd like to turn the webcast over to John. I'm pretty sure you're going to find this talk very informative. John, it's all yours.
All right, thanks, Neil. And hello, everyone. And today I'm going to be giving you guys the webcast on fundamentals of vision-based navigation. All right, so I thought I might start out by pointing out that you may not know it, but most of you are probably already vision-based navigation experts. Now, you may think to yourself, I'm not a vision-based navigation expert. If I was, I wouldn't be attending the Fundamentals of Vision-Based Navigation webcast. But so if you think about what vision-based navigation is, and maybe how you got to where you are right now, maybe how you got from home to your office this morning. If you're like most people, if you're like me, what you did is, you got up, you got in your car, and you drove to work. And as you were on your way, you used visual cues, that you got from your eyes, along with your inertial measurement unit, your inner ear, and it kind of navigated your way to work. Maybe you looked at street signs and figured out what road you were on. You used visual cues to know when you entered the intersection and when you needed to turn. Used visual cues to stay in your lane. And you also performed relative navigation to other vehicles. You navigated relative to other cars that may have been on the road, and hopefully you avoided any unintentional rendezvous with other vehicles out on the road. So, you have, I guess what I'm saying here is that vision-based navigation is something that we as humans naturally do. So congratulations. Years of experience have made you a vision-based navigation expert. Now, spacecraft vision-based navigation, the idea here is what we want to do is use the way that we as humans navigate, which is, with our eyes a lot of the times, and see how we can, leverage that experience for the navigation of spacecraft. So when I talk about vision-based navigation for spacecraft, or what you might hear referred to as optical navigation, depending on who you're talking with, what we're talking about is optically acquired data that can take a number of different forms, but today we're mostly going to talk about the use of images and using the data in those images for the purpose of spacecraft navigation. Now, when you have a spacecraft and you take an image of an object, that object could be a planet, it could be another spacecraft, a moon, an asteroid, what have you, that image contains information about two things, a number of things actually, one of which is the state of your spacecraft, so the position and orientation of the camera that captured the image. Now, it also contains information about the state of the object you observe. And again, whether that's a planet or another spacecraft. And now, passive images, just with a regular camera or whatnot, have been used for a long time in spacecraft applications for both planetary navigation as well as relative navigation, things like rendezvous and docking and the like. And as we go through today's talk, what you'll see is that modern optical navigation or vision-based navigation techniques, what you'll see are examples of both passive and active sensors. So regular cameras is an example of passive, and active sensors might be things that have lasers or something else that would help you say illuminate the object. And I will point out that when we talk about vision-based navigation, it's not always in the visible spectrum. We might use things in the infrared or in some other spectrum. So I thought a good place to start would be a little bit of historical background on what has happened in optical navigation that leads us to where we are today. So really the earliest application that I know of vision-based navigation or optical navigation for spaceflight applications was the Gemini program. So if you look at this picture here on the left, that's a handheld space sextant. So if you go way back, all the way back to the 1400s, sailors on ships have long known that you can take observations, the angle between, say, a reference star and the horizon, and use that to determine, say, things like what's the latitude of your ship. Now that same idea basically holds true in orbit. So the idea with this Gemini, with the space sextant that flew on Gemini 4 in 1965, was that they could measure the angle between a star and the horizon and use that for navigation. This particular space sextant actually flew twice, one on Gemini 4, one on 7, both in 1965. And that was really, like I said, the first application of that I'm aware of optical navigation in space. And this really paved the way for future use of the whole space sextant concept on the Apollo program. So if you look at this picture on the right, there was also a space sextant on Apollo. It was on the command module, and you see here a picture from Apollo 8 with Jim Lovell taking some sightings. So actually on Apollo 8, Lovell took over 200 space sextant measurements on the way out to the moon and was able to recreate the closest approach to the moon to within about 2.5 kilometers of the ground-based solution. But his solution was done entirely on board using only optical measurements that he collected with this space sextant. And they also demonstrated on the way back that he could use those measurements and fully on board meet the Apollo reentry requirements. So this takes us probably into the Apollo 8, for example, was in 1968. So now we're into the late 1960s, and that leads us into robotic missions. So robotic missions have used images of whatever object it is they might be going to visit to navigate for a long time. Actually, the first instance of that was 1969, just 1 year after the Apollo 8 mission. So Mariner 6 and Mariner 7, both missions to Mars, used optical navigation. What they had is the proof of concept. So that's the first time where we actually demonstrated that, yes, you can take images with a camera on a robotic vehicle at another planet. So that was Mariner 6 and 7. So just a few years later, Mariner 9, 1971 now, was the first spacecraft to actually take those optical navigation measurements and stick them in and include them in the orbit determination process. So at that point, we actually demonstrated that not just a proof of concept, but yes, you can in fact do this. So now we're 1971. So as we progress through time, and we eventually get to the Voyager missions, Voyager 1 and 2, those in 1979 now, so you can see us marching along here on our timeline, were the first missions that actually required optical navigation to meet their mission requirements. And they demonstrated that during flybys of Jupiter, again, the late 1970s. So since then, we've used optical navigation on most major planetary spacecraft you can think about. So Galileo, Cassini, Messenger, like I mentioned, the Voyagers, all of these have used optical navigation in one form or another. And typically what happens is the pictures would be captured by the spacecraft, they would be downlinked to Earth, and then they would be combined with radiometric tracking and what other data you might have available. And then the best possible estimate of the spacecraft state would be computed. Now that works great unless things are happening really fast. So say, for example, you're encountering an asteroid, some other small body, or doing a very fast flyby, and you don't really have time to take a picture, downlink that picture with the light time of flight delay, process some stuff on the ground, and then send something back. So because of that, in the late 1990s, we had some missions that really necessitated autonomous onboard optical navigation. And there are a few different flavors of this. Probably one of the most well-known one is JPL's AutoNav. But here you can see and that AutoNav was first demonstrated on Deep Space One. So you can see a picture of the of an image of an asteroid collected by Deep Space One. And like I said, there are a few different flavors of this. One would be as you fly by an asteroid, you're just trying to track the asteroid. So maybe looking at something as simple as center of brightness, and you just want to keep your instruments pointed at the asteroid as you fly by, as well as more sophisticated optical navigation, which will autonomous optical navigation, which we'll talk about later. And that again has been now ongoing since that first demonstration in the late 1990s. Okay, so here is just as a brief example, here's a number of images collected of various asteroids and comets and the like, where we have done some form of autonomous navigation during the flyby. And you can see, kind of as we might go by this thing, you have to keep your instruments on it as you move by. Many thanks to some of our good friends at JPL for providing these images. Thought you guys might like to see some pictures of some actual asteroids here. Okay, so what I've done so far now is talk to you about classic optical navigation. That was that first set, where you take the pictures, you downlink them, then you combine them and do some data fusion on the ground. Then we talked about the autonomous OpNav, which was the version where a lot of that stuff is attempted to do some of that on board. And this is just my list of missions here is not intended to be complete, more just representative of some missions. But what I want to point out is, in addition to just what the spaceflight community was doing, throughout this time, especially since the 1970s, there's been a ton of great work done by the computer vision community, largely made up of folks doing computer science for terrestrial robotic applications, and a number of other folks from electrical engineering departments and the like, developing all types of really cool techniques for image processing and what we call pose estimation. So pose is the term you'll hear me using for relative position and relative attitude. So I'll refer to pose a lot, and that's what I mean by that term. And from time to time, these new techniques migrate from that bottom list below the timeline, and they, from time to time, a few of those things get added and incorporated into spaceflight missions, the things you see on the top. Okay, so that's a little bit of a historical perspective about some past missions that have used vision-based navigation. And if you're interested in how any of these missions worked or what they did, there's some great references at the end of my presentation that you can look at for more information. So what I want to talk about now is the vision-based navigation process. So if I want to do vision-based navigation on a spacecraft, what are the things that the spacecraft has to do? And at least this is my summary. Other people may have more or less steps than me, but I view this as really a three-step process. The first step is to capture an image. So you have to obtain an image through a camera or some other device that contains an image or optical data of the thing that you're trying to measure. The second step is, now that I have this image, the image probably has noise and a whole bunch of other problems with it, But what I need to do is I have to go into that image and do some type of processing to extract some type of usable information, some type of usable measurements from that image. Usually it's just a matrix of intensity values. So if you look at an image, each image is a pixel, you have a bunch of pixels, and there's a value for how bright each pixel is. So I got to dive into that and extract useful information. Once I have that useful information, those measurements have to get put into some kind of filter that I can use to estimate my relative state, my state relative to that observed object. And depending on the types of measurements you get and what you're able to observe, sometimes an image might contain just partial information into your state, and then if there's enough features and things you can track, possibly the full 6-DOF state. So what I'm going to do for, I think, the bulk of the remaining portion of this presentation is to kind of step through these 3 steps and talk about the different variations of techniques and methods that you might see. All right, so we'll start with capturing an image. So in case you're not familiar with how cameras work, at least from the standpoint of the geometry of projection of the 3D world onto a 2D focal plane array, onto the detector. I'm going to try to go through that now so that you have some context. So a camera has a lot of components, but really the 2 main components that we care about for this application is the focal plane array and the lens. Okay, so the point of the lens, right, is to capture light and focus that light down onto a single point or a point on the focal plane array. Now you can see if you look at this diagram, you have these parallel rays of light coming in. That's to some object relatively far away, and then the lens focuses that light down. Now, there's 2 points I want to make here. First of all is that center ray. You notice the ray that passes through the center of the lens is not distorted, is not bent by the lens. We'll call that point the optical center of the lens. And at the optical center, again, that ray is not bent, which means from a geometry or conceptual standpoint, we can imagine that lens shrinking down to just a single point, a pinhole, if you will, right at where the bore sight intersects the lens. And just let that one single ray pass through, right? And that is a geometrical model of a camera. In fact, if you go back to cameras from a really, really long time ago, they actually did have pinholes. That's it. And if you were in high school and you ever you poked a hole in a sheet of paper to watch an eclipse, same kind of idea of what's going on with the pinhole. In any event, if you go look up the pinhole camera model, that's the model we're using for the geometry for our camera. Now, the next thing I want to point out is that if you look at what's going on the focal plane array, the image that is on the focal plane is flipped from reality. So you'll see what this object we're viewing in our example is above the camera bore sight, but you see it at a pixel on the bottom. So what is above appears to be on the bottom, and likewise what is on the right would show up on the left side of the focal plane array. So what happens is everything is flipped when you're looking at the image on the focal plane, which is not a big deal from a modeling standpoint, but it can be a little counterintuitive. So because of that, we introduce something called the image plane. Okay, so what I've done here is I've gotten rid of all those other rays, and now all you see is that center ray for our pinhole camera. And I've introduced this thing called the image plane, which is the same distance as the focal plane, but now it's this imaginary thing in front of the lens. Okay, and if you look at where all those rays intersect now this image plane, what it produces is kind of the intuitive picture you would expect. You can almost think about this if you had a sheet of paper that you held up in front of your face. That would be and your eye was the lens. That sheet of paper would be that imaginary image plane, and it would produce a scene with everything not flipped. Okay, so now what we're going to do is talk about this geometry a little more, and you'll see I'm going to get rid of all the stuff on the back, so the focal plane array won't be there anymore, and you'll just see me talking about the lens and then the image plane out front. So here's that 3D picture. So you see on the very far left there, the camera sensor frame. That is a XYZ frame with its origin located at the optical center of the lens. It's the pinhole, right? And again, now you see the camera image plane. And what this figure is intended to show you is, how a 3D point, so if you look at that point out on the far top right, that capital X, Y, Z, it's how that 3D point out in space projects onto the lowercase XY coordinate that you see there on the camera image plane. Now, what we're going to show is that because we set this up, you can use something as simple as similar triangles to relate the projected point, that xy, lowercase xy point on the image plane, relate that 2D point to the 3D point. So here's one similar triangle. If we want to just talk about the x direction, right? That orange triangle, which has a distance of f along the bore sight direction and a distance of little x along the x direction, that's one triangle, and that is a similar triangle to that yellow one, which has a distance of z, capital Z, along the bore sight and a distance of capital X along the x direction. So we can do this for the x direction, and we can do the same thing for the y direction, which you see in this similar triangle here. And then we just stack all that into matrix vector notation to make things a little tidier. And what you see now is I'm able to take that x, y, z, all capital letters on the right, 3D location, and then figure out what is the x, y, 2D image plane coordinate, which is the thing you see in the equation in the vector on the very far left. Okay. Now, the problem that you see with this, right, is that x and y has units of length, not units of pixels. And when I go look at a picture, what I see is everything is in pixels, not in millimeters, something like that. So I got to find a way to convert that. And this is how we're going. This is how we're going to do that. So by convention, the origin of an image is usually in the upper left-hand corner. So what I call the U direction here is the column number. What I call the V direction here is the row number. And just with a simple little matrix here, I can convert my units from length to pixels. It's these XS, SX, and SY have units of pixels per length. And you can do a camera calibration procedure will tell you what these values are. And then if I just substitute in, see that little that on the right there, that XIYI1 lowercase. If I go one chart back, I know what that is in terms of my 3D location from this matrix equation here, and I just substitute that in, and what you find is now an equation that relates a 3D location, observed point location, to a 2D pixel coordinate, which is what we want. So now we have a way of relating those two things. Now, the final point I want to make here is if you look at this equation, and if you look at this geometry, each pixel point really just gives you a line of sight direction. It doesn't give you any range information. So we'll have to attack the whole range problem in some other way, which will be a topic that we'll talk about here in a few minutes. Okay. Now, so that gives you a little context about capturing an image and the geometry of how that works, how a 3D point gets projected to a particular pixel location. Okay, so now what I want to do is figure out, I have an image, okay, and if I can find a point on this image, I know what point what direction that pixel is pointing to in my 3D world. How do I figure out where things are in the image? How do I find, landmarks or stars or objects or something useful in my image? And it turns out that this is, in my opinion, probably the most challenging part of optical navigation. I mean, the geometry of camera projection is pretty straightforward. And as we'll see later, the whole filtering problem is really well understood, and there are a few techniques that we can use to really solve the whole filtering estimation problem. So we got a really solid handle on that. The sticky point usually is how can I reliably and robustly pick out features in an image and not get confused about what features I'm picking out. So this has led people to make the problem simpler by making what we call cooperative objects. So the problem's hard, so let me put beacons or other features that are easy to detect. I'm going to try to make the problem easier by making a cooperative object. So we're going to talk about two classes of objects. A cooperative object, which is where I go out and put something on the thing I'm viewing to make this part of the problem easier. And then the non-cooperative object, which is number 2 here, which is where for some reason I can't do that. So for example, if you're doing flying by an asteroid or going to another planet or flying by a moon, you may not have that luxury. Okay, so let's start by talking about cooperative objects, which I again define as some object that I equip with markers, reflectors, or some other purpose-built, intentionally put on there optical navigation aid. And those aids come in at least 2 different flavors. The first one I want to talk about is passive cooperative targets. Okay, so this means on my object, the object I'm viewing, I'm going to put some type of marker or fiducial that I can observe passively with the camera. Now, there are a whole lot of different ways to do this. They can be as simple as, if I have an object that is basically gray and I put a red dot on it, then my finding the marker or fiducial is simple as looking for the red item. It's the only red item that's on there. Now, sometimes our real life problems have more complicated objects that we're observing. We need to be a little more clever. But one example of a passive marker that you might see is concentric contrasting circles. So an example of that is on the that circle, the target looking thing you see on the right there. That's a black circle with a white circle in the middle. Now, it turns out that these types of objects are very easy to try to pick out or to identify. You can use an image segmentation algorithm and then just look for a black segment and a white segment where the centroid of those segments coincide with each other. And then you also know that they have a certain area ratio. And those two checks make it fairly robust to pick out these concentric contrasting circles. And those two checks I said happen to be fairly insensitive to translation and rotation. So there are a number of examples of applications of this particular feature. Actually, a few in spacecraft. One example, and this picture is at least a little smaller on my screen than it was when I was first trying this out, but if you'll actually look at the ISS, you'll see there's a lot of dots stuck all over the ISS, and you might have asked yourself in the past, why have we stuck these dots all over the ISS? And the answer is the space vision sensor, which was developed by Neptec, which is a Canadian company, and they use this type of, they look for this type of feature to compute pose on the arm. Okay, so the next type of feature I want to talk about, so that's an example of passive. So let's talk about active. So here's, I want to talk about an example of an active, and I say cooperative system, because here the target isn't or the marker isn't the active thing. So probably the most common active marker that I'm aware of is a reflector. There are a number of situations where you can use reflectors as active markers. Another option might be to actually put LEDs that blink on your vehicle, on the vehicle you're observing, and then you can look at these find the blinking lights, and that can help you navigate. But probably at least in my opinion, one of the coolest examples of cooperative systems is the Advanced Video Guidance Sensor, or AVGS, developed by NASA Marshall. And the way this system works is you put reflectors on your object, and then you take 2 images. Now these reflectors have a filter on them, and then those filters pass light at some wavelengths and don't pass light at other wavelengths. Now, if I then have a laser that shoots at 2 different, and I can illuminate my scene at 2 different wavelengths, one wavelength that the filter passes, one wavelength that the filter does not pass. And if I do that sequentially real fast, I'll get 2 images. One that includes the reflectors because the light passed through that filter, and the other that does not include the reflectors because the filters blocked that laser light. And then I get these 2 images like the ones you see on the left and on the right here. Now this is kind of like, if you just look at these 2, it's kind of like those cartoons you see in the newspaper where they have 2 pictures and they ask you to find what's in one picture but not in the other picture. So that task might be hard for humans, but it's fairly easy for a computer. All you actually have to do here is subtract these 2 images. And when you do that, you get this image on the right. And those of you with really good eyes can see those 2 little spots there on the image on the right. Those are the reflectors that have been picked out by the AVGS. And for people who are more interested in more information on this particular system, there's a really great reference in my list of references that talks about this in much, much more detail. Okay, so those are 2 examples of cooperative systems, one using a passive marker or fiducial, and one using an active system where you illuminate it with a laser. Now, life, unfortunately, is not always so easy. We may not be able to go put these features or markers on the thing we're going to go rendezvous with or attempt to navigate relative to. This is the case for most planetary spacecraft, planets, moons, asteroids, comets. We usually can't do that kind of thing. This is also true if you want to try to go rendezvous, say, for repair refueling of a legacy spacecraft, say a older spacecraft that you didn't put these things on before you launched. In this type of situation, we need to be a little more clever, and this is where we're gonna go now. Now, when you approach a vehicle or another a moon or asteroid or something, when you're far away, that object is small, right? So when you first start to see it, it's only going to subtend a few pixels, right? It's just going to be a little spot. And when you're that far away, really the best that you can do, and really all we do, is you just try to centroid that object. Okay, so it's just a little spot. So we look for trying to find the center of that spot and then compute the bearing to it, the azimuth and elevation, or any number of other ways to parameterize that. The space shuttle used this for rendezvous and docking. It would make passes with the star tracker and take centroids to like the ISS or whatever it was rendezvousing with. And this has been used for navigation, I think, for AutoNav, for example. Use this centroid and bearing kind of approach for asteroids and whatnot when they were far away. But there are a lot of applications for this. Now, as you start to get closer, what's going to happen is that object's going to get bigger. And instead of only subtending a few pixels, it actually start to be a resolved object that takes up a whole bunch of pixels. At that point, we need to look at a different way of handling these points. Oh, and I should point out before I go on, just as a go back for a few seconds here, as far as techniques for doing this, two real common ways are template matching, like normalized cross correlation is used quite frequently. Same kind of thing that's used in to find stars, which look like small points too. As well as if the thing's sufficiently bright, you could use something as simple as thresholding. But in any event, as you get closer, it will get larger, and you need to do something more sophisticated. Now, one aside, because we'll talk about this more coming up, is a lot of things project to ellipses. If you have a circle, such as circular things that in space include things like craters, they include things like Marmon rings and docking rings and everything's being launched in launch vehicles, which are circular. So there are a lot of circular features on spacecraft. Those circles project to ellipses. Also, spheres. So spheres project to ellipses. Planets, a lot of planets and moons are very nearly spheres. In fact, we can model them more accurately as triaxial ellipsoids, and it turns out that both spheres and triaxial ellipsoids project to ellipses on the image plane. So all of these things, circles, spheres, triaxial ellipsoids, all project to ellipses, which means there are a lot of great applications for ellipse detection algorithms for optical or vision-based navigation. And if you want a really great discussion of how to take ellipses and then compute some information about the relative state of the thing that you're observing, this paper here that I referenced, reference number 29 in my list of references, is a fantastic discussion. It approaches it from looking at these as conic sections. And you can actually see in this picture how these circles and ellipses are just different sections of a cone, with the vertex of that cone being at the lens optical center. So we will discuss the use of ellipses a number of times here coming up. Okay. Now, what I want to discuss at this point is relative navigation to planets, moons, and asteroids. So say we're approaching an object, and I want to separate these a little bit from other navigation relative to other spacecraft, so we'll come back to that. But as you approach these objects, they start to become resolved, and I want to talk about, again, relative navigation to these types of naturally occurring objects. Now, there are a number of ways that people have extracted measurements from images of planets and moons in the past. Three of the main ones that I want to talk about are star horizon measurements. This is effectively the image-based equivalent to what we were doing with the space sextant, right? The space sextant, it was the angle between the star and the horizon. Same thing here. Now we're just going to do it in an image. Okay, that's this first measurement. The next is centroid and apparent diameter. You're going to centroid the object, and then figure out how big it appears to be in the image. Okay, and then the third one is surface feature tracking actual points on the surface of the observed body. Okay, so let's start with star horizon. So let's say I have a picture containing a let's say, a moon and a star, and that it's kind of like you see in the upper left there. Okay, you can get from your image the angle, the scalar angle between the star and the horizon of that particular moon. In this case, we're talking about a moon. Now, those stars are, the stars you observe are very, very, very far away, right? Which means as I move, the direction to the star doesn't change a whole lot. Now, what that means is if you look at this little picture here on the right, just with the little rotation circle in it, what that means is if you look at the angle that you measure there between the star direction, the dotted line coming off my little PowerPoint Orion, that dotted line there is the direction to the star as viewed by Orion. And then you have that direction to the star is basically the same at the moon that you observe. And that scalar angle is that line that you see there between the red line and that dotted line. Now, if you were to flip this image and you put Orion, my little cartoon Orion, on the other side of the moon, you would have the same picture. In fact, you can revolve this around the line of sight direction to the star. What that means is when you take a scalar star limb or star horizon measurement, what you get is a cone of position, like you see here on the image on the right. The spacecraft will lie somewhere on this cone, with the axis of revolution of the cone being the line of sight direction to the star that you picked out. Now, if I take now the observation to a second star, I will get a different cone, and then I'll have the intersection of two cones, right? One formed by the red star, one formed by the blue star in this picture on the right. What that means is my spacecraft is on one of two lines of position now instead of cones, the intersections of the cones. Now, if I measure 3 stars, 4 stars, 5 stars, maybe I can get rid of one of those ambiguities, but at most, what I'm going to get is a line of position out of this type of measurement. But this is the star horizon measurement. It is probably one of the more popular measurement types and has been used extensively in past missions. Okay, the next type I want to talk about is centroid and apparent diameter. Here you see two pictures of, in this case, it's a Venus from the Messenger spacecraft. Just looking at these, you know we are closer to the moon, or in this case, sorry, the planet, in the picture on the left than we are on the right because it appears larger. And I can use that apparent size to get an estimate of range. Now, it may be a fairly poor estimate of range, but an estimate of range nonetheless. Now, you can also take this and fit an ellipse to it or do some other type of fitting and find the centroid. And that will give you that direction plus that range, like you see here, will give you an estimate of your 3D position relative to the planet. And you know which way that vector is pointing because presumably you have star trackers or some other type of sensor on board to compute your inertial attitude. But this is the concept behind centroid and apparent diameter. The size tells you how far, the direction to the middle. Well, it's not the middle of an ellipse. Just for reference, does not actually point toward the center of the actual planet. It's actually offset. But in this case, the size again is your range, and then more or less the center tells you what direction the planet's in. So two examples of this. This is some examples from reference 6 from my list of references. It's from a paper I wrote a number of years ago, where we're looking at centroid and apparent diameter. And this is examples using Venus and Mercury, and again using ellipse fitting. Okay, so the third technique. So we've talked about star tracking. It takes a number of different. Again, there's a number of flavors of this, but one good example is crater tracking. So if you go look at the moon, or if you look at images of the moon, there are a lot of craters, and we have catalogs of those craters. So a number of people have looked at using an ellipse detection algorithm to find craters, and then now I have a bunch of craters in an image in some pattern. Then I match that pattern of craters to a catalog of craters using your position. Similar technique was also done on NEAR. to navigate using craters relative to the asteroid Eros. So those two references, 16 and 28. 16 will talk about using craters, landmark tracking of craters for the moon. 28 will talk about use of craters and ellipses for craters for navigation of near relative to the asteroid Eros. Now, I'll point out that the landmarks you use are not just limited to craters. There are a lot of really interesting and a lot of interesting features other than just circles and ellipses. This is an image, 2D pattern of on the surface of an object. Maybe that's due to the different albedo or whatever it is that you're observing. As long as there's a unique kind of 2D pattern, you can use that as a feature. And references 13 and 14 have some great examples of how to use features, design features that aren't tied to things like craters. All right. Now, as I guess as another example, so this is again using landmark tracking. So if you have a space, these results here are for a spacecraft in low lunar orbit. So it's say I think a 400-kilometer altitude low lunar orbit, and if you can have relatively well-spaced features, what this shows you is you can get a more or less steady state kind of. But this is from a paper from last year, looking at totally autonomous optical navigation in low lunar orbit. Okay, so that really is it for at least what I was going to talk about for planets and asteroids and moons and the like. Now, the same kind of problem is also true for other spacecraft. So say you want to go rendezvous with some legacy spacecraft because you need to repair it, refuel it, or what have you. So there are a number of techniques, and we were just talking about feature tracking using craters and the like. Now you can also track other kinds of features. So say I'm going up to a spacecraft and I have a model of that spacecraft. I can go. So this example here is for natural feature image recognition, and the idea is I have this model and I know where features are on my model, so I can go into my image and then extract edges. Edges for, in this case, this is a picture of Hubble. So you could extract solar array lines, different locations of thrusters or panels or other known features that are going to create nice lines, right? So when I go to edge extraction on right, there's going to be some disagreement between the edges that I measure or I observe and where I expect those edges to be from my model. And then what I can is into better agreement, and that will tell me how much I need to update my the estimate of my position and attitude. So the images you're seeing here are from some folks at NASA Goddard from the Satellite Servicing Capabilities Office, and both these and the ones that you see here. This one is the Goddard Natural Feature Image Recognition, or GNFR, results from tracking the Hubble Space Telescope during STS-125. I think some of this is, and what you can see here are the actual images overlaid with these dots of points where they're kind of tracking these edges of features that they've modeled. Okay, so that is it for extracting measurements from images. So just as a quick recap, what we've done is looked at different ways to extract measurements. We talked about for things far away, just centroiding. As you get a little closer, various types of ellipse fitting, either for planets or craters or the like. Then we talked about star horizon measurements, talked about centroid and apparent diameter measurements, and then about What was the third one? Now it's escaped me. Oh, I'm going to have to go back. And landmark tracking. And then finally, natural feature image recognition. All right, so now we'll move on to filtering. So once we have these measurements, now our task is to filter them, to combine them either with other optical navigation measurements or with other things like IMUs and the like. So there are at least 4 paradigms you might run across. The first one here is what I'll call ground-based batch estimation. This is kind of the classic optical navigation where I take those images, combine them on the ground with radiometric tracking and whatever else I have available and compute the state. 2 through 4 are variants of onboard vision-based navigation. One using just centroids and bearings. This is for if you never get real close and you're just using things far away. Number 3 is filtering many points. So say I observe like a lot of reflectors, have line of sight to lots of reflectors, some other fiducials on my observed object. I can stick those directly into an EKF. And 4, which is a variant on 3, rather than taking those different measurements and putting them directly into an EKF, I can actually take them and combine them separately and compute pose all by itself, compute the relative position and attitude, and then take that pose and filter the pose in an EKF. So we will talk about these in a little more detail now. Now for that first one, or excuse me, for the second one here, where we're talking about bearings, there's an important point to make, and that is some observability challenges. If you're just computing centroids or bearings to an object that's pretty far away, a camera doesn't provide range. So that's what I'm trying to show here in this picture. You don't know whether that spacecraft that you're observing, that little point, is close or far away. All you know is what direction it is. Now, it turns out that if you're doing relative navigation, say in orbit about Earth or whatnot, to some other object like this, your relative motion is described by the Clohessy-Wiltshire equations. And when you actually put this into there, what you'll find is you don't know exactly what your trajectory will be. There's a observability problem. You don't know whether you're in a say you're in a making a circle around this target object. You don't know whether you're going a small circle very fast or a big circle big circle slower. Both provide the same time history of line of sight. So there's a really good discussion of this by Wolfenden and Geller in reference number 32 that I would recommend. Now, there's a few ways to solve this problem. They talk about in this paper you can perform maneuvers and get rid of this observability problem. But the other ways are you can get close enough to actually measure multiple points and use those multiple points to compute range, or you can have a LiDAR and actually directly measure range. But if you're close enough, you can measure multiple points, and then you can actually just compute pose. So what you see here is this diagram here is to show you that you have your camera frame and your pose, your relative position and orientation is described by 2 things. R, it's the relative position of this object relative to your camera, okay, and T, the rotation matrix that describes the rotation from your the object body frame to your camera frame, okay, and it turns out that the solution to this pose problem is fairly well understood, and there are a number of ways of solving it. Now, the difficulty is this. The difficulty is that we actually don't get that YI there. We don't actually get the 3D location of that observed point in the camera frame. All we get is the 2D point, the projected 2D point on the image plane, that UIVI, using that equation that we saw before. Okay, so we got to figure out, if I just have this group of 2D points, how do I get my 3D pose? Now, there are a handful of, what we'll do is we'll do this in two steps. Now, there are a handful of ways to compute pose if you have sets of corresponding 3D points. And they're listed here. Here are 3 very common ones. Singular value decomposition, reference 17 has all the details. Horn's method or Q method, reference 20, and then a Cayley transform method, reference 22. Now, all of these work, but all of them have their pros and cons. And for the sake of time, I won't go into all those pros and cons. If you have questions about them, you can talk to me later. But I will point out that these solution methods are all parallel the attitude estimation problem quite closely. Now, the trick is those required 3D sets of corresponding 3D points. What you were missing there was range. So the way we solve this usually is we take the 2D problem, take those 2D image points, and then try to find some way to figure out what the range should be to those points. So now we have 3D points, and we apply the things I just listed. The 3 ways to tackle that problem: posit, which is anyone who uses OpenCV. If you use pose in OpenCV, posit is probably what you're doing. Triangulation. There's some nice closed forms triangulation methods for sets of 3 points that require a solution to a quadratic. And then there's this Harlech method, which is an iterative method. And again, here you can see the references there if you want to read up on them. Okay. Now the other way. So here in this list, the way we were getting the distance to those 2D points is through one of these methods: posit, triangulation, or Harlech. There are ways of using the geometry between the points you observe to get range. The other way to get range is just measure it directly, and you can do that with the flash LiDAR. So the way a flash LiDAR works is so this is an example of an active sensor. Okay, so what I'm going to do in a flash LiDAR is pulse a laser at a known time. That laser is going to go out and illuminate a whole scene. It's going to paint the whole object, hopefully, with this laser. And that light's going to then bounce back off of that object and then come back and hit a focal plane array. And at each pixel, I have a timer. And I know the time that elapsed between that laser pulse went out and when that laser pulse came back at each individual pixel. That gives me a range at each individual pixel. And then I can use that range as a different way, if you will, of getting that range information that I would have gotten through one of those methods that I just described. So as some examples of a flash LiDAR, there is the Vision Navigation Sensor, or VNS, that flew on, there was a DTO of that on STS-134. And this is the type of thing you'll get. So out of a LiDAR, right, you'll get 2 things. You flash that laser, the light comes back, you get an intensity image, kind of like a black and white image that said about how bright the laser was. And then you get a point cloud. You get range at each pixel. Each pixel points in a certain direction. Multiply the range by that direction, and you get a 3D point cloud. So here's a kind of a visualization of that. Now, as far as how to use this, it works really well in a cooperative environment. So we talked about reflectors, right, for AVGS. You guys might recall the AVGS where we had where you're able to easily find the reflectors. You can do the same thing now with something like the VNS. So here's a picture of the International Space Station. It's the docking. You see there's the docking ring with these reflectors. You see these 5 reflective elements here, and those are those 5 spots kind of in the middle of that ring there. We pick out those reflectors. You can use those reflectors to compute pose using any of the SPD method, the Q method, the Horns method, or the Cayley transform method. Any of those would work equally fine. All right. So in summary, what we've talked about is a real quick high-level description of vision-based navigation. We talked about how you use optically acquired data, images, for the purposes of navigation. What you may have picked up on, again, is that the images contain information on both the state of your vehicle or your camera, as well as the state of the thing that you observe, be that a spacecraft or another asteroid or moon. You saw examples of both active and passive sensors. And we listed a whole long list of missions that have used passive images for planetary navigation as well as relative navigation. And then you saw some examples of cooperative targets using concentric contrasting circles, the reflectors for AVGS, and then the reflectors again for using something like a flash LiDAR, with the intent there to make the image processing task easier and less prone to being confused. And that is it. Now, what I want to do is I mentioned a bunch of references. So what I want to do is just kind of flip through these, leave it on the chart up for a minute. So if you're replaying this at home, you can kind of pause it on the reference slide of interest to you and write down the reference and then continue. I'll point out a few references of note here as we go through. So here, reference 9 and 10 has some great stuff on POSIT, which is the OpenCV pose algorithm. So reference 11 is a really good computer vision textbook that I would recommend. 17 and 18 also have very good pose algorithms that are worth reading. Reference 21 is a reference on AVGS. Reference 24 is another really good text on computer vision from the computer science community. Reference 26 and 27 are very good overviews of optical navigation, the kind of the classic optical navigation that you might see at JPL for planetary missions. Reference 29 is your reference on circular features and whatnot in ellipses. Okay, so that is it. Thank you so much for your time, and I'll take questions.
Well, John, that was quite a tour de force on the fundamentals of vision-based navigation. Thanks for sharing your knowledge and your insights there. I appreciate it. I'm sure the audience does too. Very interesting. I've got at least two questions I think we have time to answer here. Let me start with this question that comes from Johnny Cooper, and it's has to do with attitude versus position determination. And it goes like this. He says, I'm used to vision-based attitude determination. Is vision-based navigation also used for position and orbit determination? Are attitude and position determination done separately, or are they wrapped together? Do you want to take a crack at that?
Yes. So I assume he's the question was about, say, using cameras for things like star trackers and the like for attitude estimation. But yes, so we do use cameras for both position and attitude. So a lot of the examples I talked about today, say for relative navigation, you're actually computing 6-DoF pose. Now, depending on the application, you may or may not want to filter position and attitude together. Frequently, they are separated, but sometimes they're done together. People kind of fall into two camps on that one, and that's just kind of a general filtering thing. Some people like to put them together, some people like to keep them separate. But when you are doing pose, your pose algorithms, like if I go back one or two charts here, let me just point out some algorithms here, because I did kind of fly through these. The singular value decomposition, Horn and Cayley's method, all will solve the full 6-DoF pose, and they'll all solve them without linearization. Well, so I should point out the Cayley transform method is a way of linearizing rigorously linearizing the nonlinear attitude estimation problem. But the drawback of that one is you use the Gibbs vector, which has a singularity at a rotation of 180 degrees. But the first two actually solve the full-blown nonlinear problem, either through SVD in the first one or through an eigenvector eigenvalue problem in the second one, and you get together the full 6-DoF, simultaneously solving for position and orientation. Thanks,
John. Mm-hmm. Let's see. I have another question here, and I think it relates to chart 15.
Yes.
You touched on this. It's the idea of going from how do you get to the pixels, I think. So this comes from
Sure.
Marina Gandlin, I should say, out at Ames. And the question goes like this. U sub P and V sub P in the real world, I guess mapping those in the real world to the pixel matrix. Basically, the question is, how do we get these elements? So maybe you could walk us. You did touch on that. Maybe you could walk through that again.
That's a great question, and it's not in my references. So there's a paper by Zhang, and I can't. If you can send me,
I will send you all the questions.
Email. I can
Sure.
actually reply with the full reference. I don't remember the exact paper title, but the basic idea, what you'll do is take images of a checkerboard pattern, usually. And what you can do is you can actually estimate. You do a least squares estimation, and you estimate SX, SY, UP, UV, and actually, you see that 0 between SX and UP? There's actually a number that goes there in case the U and V are not exactly perpendicular to each other, if there's a little bit of skew. And that's called there's a camera calibration routine. So if you if you actually do a search for MATLAB camera calibration toolbox online, you can get the MATLAB version. If you use OpenCV, it's already built in, and it uses the same algorithm by the exact same author using the paper that I just mentioned. So in practice, what you'll do is UP and VP, unfortunately, are not usually in the center. They're not in the center of the focal plane array because, if you just think about when you manufacture this thing, it doesn't take a whole lot of movement, right, for the bore sight to not hit right in the middle. So you actually need to compute UP and VP. And those algorithms, those toolboxes will do it for you, and there's a great tutorial for the MATLAB camera calibration toolbox if you want to go try to do that.
Yeah, well, maybe you could add that Zhang reference, that paper, to your overall list of references, and then I will send you these 2 questions we received, and I think that's really probably all we have time for this afternoon. If I do receive any other questions, I'll pass them on to you, and I think, like we talked about before, you've agreed to follow up and answer those questions, so I appreciate that.
And people can always email me directly at
right. Yeah,
that
we'll start
email.
here with your, yes, perfect. Well, okay, so I think that was a good way to spend an hour, better than some. I just want to say, as I usually do when we wrap up, the team and I that pull these webcasts together, we are soliciting feedback on this particular webcast and also on the overall nature of these NESC, GNC, TDT webcasts in general. So I think shortly an email will be sent out to all the registered webcast participants. It'll provide you a link to what's a fairly brief, simple online survey form so we can collect your feedback. So please be on the outlook for that, and please take a few minutes to provide us with some of your constructive feedback. We welcome that. There will also be another email going out. This will go out to the entire NASA GNC community practice, as we understand it, and it will provide a link to where John's recorded webcast can be viewed online. That'll take a little bit of time to get that packaged up and put out there, so it won't be tomorrow, but you will be receiving that email telling you where to go if you want to review it again at your leisure. Let's see. I think it's kind of cool that at our next NESC GNC website, we're going to build on what John's been talking to us about today. Andrew Johnson from the JPL will be addressing so-called fundamentals of image processing for terrain relative nav, or TRN. And that next webcast is scheduled for Wednesday, the 16th of April. So if you liked this one, tune in for that, and I think we'll be drilling into a similar but slightly different area. We are planning our future webcasts to address topics of general interest to the GNC community of practice. We have webcasts now lined up essentially through the end of the calendar year. But if you have ideas for other GNC webcast topics, or even better, if you are interested in presenting your own GNC webcast, why don't you contact me directly? I'm always on the lookout for new and interesting topics and speakers. At any rate, that completes today's NESC GNC webcast. Thank you for participating with us, and I look forward to you joining us again in April for our next webcast event. Goodbye.